students, once again I welcome you to this course on microprocessors and microcontrollers. In the last class, I have given the relevance of this particular course, and we have discussed various issues which we have to cover in this particular course, and I have given an outline of the course, what will be taught in this particular semester. As you have seen, microprocessor is nothing but a central processing unit on a chip. In other words, microprocessors are used to realize computers. So, to understand the function of microprocessor, we have to know little bit about the architecture of a computer system. So, today, before I introduce to you the architecture and organization of 8085, I shall briefly give an overview of the structure of a general purpose computer. Here is the top level structure of a general purpose computer. Here is your computer system. If you blow it up, you will find that inside the computer there are several subsystems like CPU, central processing unit, the memory devices, different types of I/O devices, input-output devices or peripherals, and then there should be some way to interconnect them. So there is some mechanism for interconnection. You may have heard the name of the father of this classical computer. His name is von Neumann, and that's why the classical computers, the architecture of the classical computers are known as von Neumann architecture. So let me briefly introduce the basic functions of a von Neumann architecture. The basic characteristics are, in case of von Neumann architecture, we will find that both data and instructions are stored in read-write memory. And let's assume this is your read-write memory. This read-write memory, the contents of this read-write memory, where you will store data and program. A program, as we shall see, a program is nothing but a set of instructions, and both data and programs are stored in read-write memory, and the contents of this read-write memory are accessed by location. For example, this is location 0, this is location 1, this is location 2, and so on. In this way, a memory may have n memory locations, and in these locations you can store data as well as program. Now, the program, which is nothing but a set of instructions. Instructions are accessed and executed sequentially. This is the typical characteristics of a von Neumann architecture. And since you are storing both program and data in the memory, it is also called stored program computer or stored program architecture. Now, in this memory will be storing data and program. How they will be executed? You will require a subsystem, as I have already mentioned, the CPU. CPU will be required. This is the CPU, and also you will require various input output devices or peripherals. The CPU, memory, and I/O devices are interconnected with the help of what is known as system bus. This is your system bus through which the both memory and input output devices are interfaced. Now, the central processing unit is responsible for sequentially fetching instructions and data from the memory and store it temporarily inside the CPU and then execute one after the other. The results may be stored temporarily inside the CPU or maybe again stored back in the read-write memory itself. This is how the von Neumann architecture works. And a typical microprocessor is nothing different from this particular architecture. Only difference is this CPU, which I have shown in the previous diagram. This is your CPU. Here it is replaced by microprocessor, because microprocessor is nothing but CPU on a chip, as I have explained in detail in the last class. Microprocessor is nothing but the central processing unit on a chip. All the functionalities of a central processing unit are stored, are realized or implemented inside this integrated circuit, and this we call microprocessor. And just like the classical von Neumann architecture, here also you will require memory. We will also require various input output devices which are to be interfaced to the microprocessor through the system bus. Through the system bus they will be interfaced, and then CPU will interact with the memory and input output devices. Let us have a look at the different components which are present inside the microprocessor. In other words, what are the different subfunctions that are present inside the CPU? We will require a set of registers. As I explained earlier, the function of a general purpose computer, the instructions and data which are stored in the memory are fetched to the CPU. Then inside the CPU they have to be temporarily stored. These are stored inside these registers. You will require ALU, arithmetic and logic unit, which is responsible for processing the data. That means ALU is used for performing data processing. The ALU name has come because it can perform various arithmetic operations, logical operations, and with the help of that, data processing will be performed. Then you have got timing and control unit. This timing and control unit is responsible for coordinating and control the activities within the CPU and also control various memory devices and input output devices, as we shall discuss in detail. Now, the CPU is inside the chip, inside an integrated circuit, but for its functioning it has to interact with the memory devices, it has to interact with the input output devices, and for that purpose it is provided with interface section. This interface section is nothing but a set of pins through which it is connected to the system bus, and system bus in turn is connected to memory and input output devices. So you will see that in the last 3-4 decades we have microprocessors of different functionalities, different capabilities, but irrespective of the different functionalities and capabilities, this basic functionality that I have explained, that it is nothing but a CPU, that has remained unchanged. And so once you understand one microprocessor, it will be very easy to understand any other microprocessor, and that's why we shall focus on one of the simplest and possibly the most popular microprocessor, which is 8-bit microprocessor, that is 8085. Let us focus on different sections of the CPU. First we shall focus on the register section. You may be knowing what is a register. A register is nothing but a set of flip-flops which are used to store instruction data, and obviously the number of flip-flops will depend on what is the size of data, what is the size of instruction, what is the size of address you will be storing. In case of 8085, you will see most of the registers are 8-bit because it is a 8-bit processor. Size of data is 8-bit. The registers may be broadly classified into two types. One is general purpose, and by general purpose we mean that these registers have not been explicitly used to store a particular type of information. These registers can be used to store data, to store address, and as a consequence the name general purpose has been given. And you will find that the number of general purpose registers and the number of bits in different registers will decide its functionality, and the number of general purpose registers which are available inside a particular microprocessor will decide the size of the program. That means to implement, to realize a particular task, how many instructions you will require. That will be decided by the number of general purpose registers available to you, because you will see that intermediate results need not be transferred to the main memory. As a consequence, more the number of general purpose registers available to you, it will be possible to write a program with smaller number of instructions, and also the execution time will be decided by the number of general purpose registers. And thirdly, ease of programming. Ease of programming will be also dependent on the number and type of general purpose registers that we will be having. Later on we shall illustrate with example and see how the number of registers available, general purpose registers available in a microprocessor, affects the size of a program, that means the space, execution time, and ease of programming. And obviously, as I told, the size of the number of bits will depend on the word size of the processor. Word size, in case of 8-bit microprocessor, it is 8-bit. But usually, uh, you have to store the address also inside these registers, and you will find that most of the 8-bit microprocessors are provided with 16-bit address. So you have to devise some mechanism by which you can store that 8-bit data as well as 16-bit address using the same registers. And later on we shall discuss the concept of register pair, by which the same set of registers can be used to store address as well, which are 16-bit. Then there is another category of registers which are known as special purpose. These special purpose registers, as their name implies, are typically used for some specific function, specific purpose. For example, accumulator is a special purpose register. Program counter is also a special purpose register. Accumulator is commonly used to store one of the operands that will be processed by the by the ALU. So one of the operand will always come from the accumulator, and program counter keep tracks of the memory location. As I was telling, the instructions are accessed from the memory, which are addressed by memory locations. This address is generated by the program counter. Then you will require status register. Status register will reflect the outcome of an instruction execution. Whenever you execute an instruction, the outcome of that instruction execution, whether there was any overflow, whether there was any result is positive or negative, whether what is the parity of the result, all these status information is stored in this status register. Then another useful register is stack pointer. Stack pointer is used to implement one very important data structure. You may be familiar with the data structure stack. You have seen stack is used for various applications, particularly for interrupt handling. Whenever you are performing subroutine call, you will require stack to store uh, uh, the information that you will require, which will be used after returning from interrupt or after returning from subroutine call. And that's why in most of the microprocessors, stack is implemented with the help of a stack pointer. We shall discuss about it in more detail later on. Now, another way of classifying registers is whether they are user accessible or not. The registers that we have discussed so far, for example, these general purpose registers, the special purpose registers that you have mentioned, that is your accumulator, program counter, status register, stack pointer, all these are user accessible. By that I mean, with the help of program, with the help of various instructions, you will be able to access them, you will be able to read them, you will be able to write onto them, onto these registers. So that's why it is called user accessible. But apart from these user accessible registers, there are some registers which are provided inside the microprocessor which are not user accessible, but but uh, but at the same time they perform some useful function. For example, uh, memory address register, memory data register, instruction register, temporary register. These are not accessible. These registers are not accessible to the programmer. That means programmer cannot access them, but nevertheless they are inside the microprocessor and they perform useful function. Memory address register is used to hold the address before it comes out on the address bus for accessing memory and input output devices. Memory data register is used as a buffer register to store the data which is accessed through the system bus, which are read from the memory and input output devices. An instruction register is used to temporarily hold the instruction before it is being decoded and executed by the microprocessor. And temporary registers are again used to hold some intermediate result which is applied to the ALU or other functions. So this is the overview of the different types of registers that are present in microprocessors. In case of 8085, you have got several registers. I shall briefly discuss about them. But 8085 has got number of general purpose registers and some special function registers. For example, it has got accumulator 8-bit because it is an 8-bit processor. Then you have got several general purpose register B, C, D, E, H, L. These are all general purpose registers. Now, as I told, general purpose registers are used to hold data as well as address as and when they are required for different purposes. Now, whenever you are holding or storing data which is 8-bit in case of 8085, you can access them individually, B or C or D or E or H or L. But whenever you have to store address which is 16-bit, how do you store? You will require 16-bit register. Then these registers are accessed as BC register pair. Register pair. So B and C together gives you BC register pair, and then it can hold 16-bit data. Similarly, you can access D and E together as D register pair, HL register pair. So 3 16-bit registers are also available, which are combination of these individual registers. That means you can individually access them when you are storing 8-bit data. You can access as register pair when you want to store 16-bit data or address. Then you have got program counter, which is 16-bit. Since as I told, the size of the address is 16-bit, the program counter has to be of 16-bit. Stack pointer, since it points to a memory location, stack is implemented by a part of the main memory, and stack pointer points to that memory location and or the bottom of the stack, and that's why it should also be 16-bit. Then you have got that program status word or the flag bits. You have got several flag bits S, Z, SC, B and CY. Let's see what are their functions. CY stands for carry. Whenever there is a carry output after the execution of an instruction, this flag bit will be set. P stands for parity. It reflects the parity of the result even or odd. SC, this is your auxiliary carry. Sometimes you have to implement processing of 4-bit data. So carry coming out on the from the fourth bit, that means 0, 1, 2 and 3. From that bit, if there is whether carry is coming out or not, that is reflected in this auxiliary carry bit, flag bit. And then you have got Z, whether the result is 0 or not, and S stands for sign. What is the sign of the result, whether it is positive or negative? If it is positive, that most significant bit of the I mean the output of the accumulator will be 0. If it is negative, that most significant bit will be 1. That is reflected by this sign flag bit. Later on you will see these flag bits are very important for implementing various types of control loops for decision making, and they are very useful in writing programs for different applications. Now let us focus on the second unit, that is your ALU, arithmetic and logic unit. What the ALU can do, as the name implies, the arithmetic and logic unit performs some arithmetic operations and logical operations. And as you know, the arithmetic operations are addition, subtraction, multiplication, division, then your increment, decrement. These are all arithmetic operations. However, a subset of different arithmetic operations are available in different microprocessors. For example, when 8085 was introduced, the arithmetic and logic unit capability were very restricted. But in present day microprocessor, you will find lot of arithmetic and logical operations are provided. For example, in 8085, the arithmetic operations which are provided are nothing but very few: addition, subtraction, increment, decrement. These are the only arithmetic operations which are provided in 8085. Obviously, whenever you have to implement multiplication or division, you have to write a program. You have to implement it with the help of a software, and you will do it in your lab. So far as logical operations are concerned, it can perform various logic operations like AND, OR, XOR, NOT, clear, compare, shift, rotate. These are the various logical operations the ALU of 8085 can perform. And obviously in modern microprocessors, the logical operations will be more. Other logical operations can be performed. And moreover, the arithmetic operations which are performed are restricted to only 8-bit data. That means if you have to implement, say, 16-bit addition or 32-bit addition, again you have to write a program. It cannot be done directly by executing an instruction of 8085. So this is the capability of the ALU. Now let us focus on the interface section. Before we discuss the timing and control unit, let us focus on the interface section. Interface section uh, is decided by technology as well as by the commercial aspect. For example, the number of pins that is provided by a microprocessor is dependent of the technology of that date. In the early years, integrated circuits were available with only 8 pins. Then later on, 4 pins, then with 8 pins, 16 pins, 24 pins, 40 pins, and gradually it has increased. Because the more the number of pins, more costly is the IC. So the cost of an IC depends on the number of pins, and also you have to see whether the technology of that day, whether it can support it or not. When 8085 was introduced in 70s, in those days 40 was the optimum number of pins which was supported by the technology. So you have to accommodate all the pins, all the signal lines that you require for interfacing with the external world. By external world, I mean memory and input output devices. So they were provided with, supported with only with the help of 40 pins in 8085. And nowadays you will find there are many microprocessors which are having as many as 256 pins or more, because the requirement has increased, technology has advanced. But let us focus on what is provided in 8085. But the nature of the interface section has not changed over the years. For example, the interface section will provide a number of pins or lines which can be broadly divided into 3 types: memory and IO control lines. Memory and IO control lines, like say read or write. Whether the CPU intends to perform read operation or write operation, because it is generating a signal which is applied to the memory or input output devices. So ALU or the CPU has to convey to the outside world whether it is performing or the instruction that is executing is for read or write. So that is conveyed with the help of read write pin. Or you will see that there are some microprocessors in which the address that is generated can be for either for memory or for IO. So at a particular instant, the CPU is accessing memory devices or input output devices. That CPU has to convey. That means whether it is executing an IO instruction or a memory instructions, memory read or memory write. That has to be conveyed by another pin, that is IO by M. That means whenever this line is 1, it corresponds to IO access, and whenever that line is 0, it is for memory access. Then it can be, there is another line, ready or wait. Later on, when we shall discuss memory interfacing, you will see that there is some incompatibility. There may exist incompatibility between the speed of CPU, the microprocessor, and the memory devices, but they should work in a synchronous manner. Whenever the CPU is reading some data from the memory, it should read correct data. So for the purpose of synchronization, some signal is provided, which is an input pin to the microprocessor, which is known as ready wait. That means it is used to provide, it is used for interfacing slow memory or input output devices. The memory devices need not be fully compatible in speed with the microprocessor. To facilitate that, this pin is used. Then another pin is provided, that is address latch enable, ALE. You will see that to optimally use the number of pins provided by the microprocessor, sometimes same lines are used for dual purpose, for address as well as data. So it has to be conveyed to the outside world again. that at that instant whether those lines are having address value or data value. And ALE, address latch enable gives you that information. That means at that instant it is having address which should be latched in some outside buffer and to be used in the next subsequent time. Then apart from these lines, some status lines are provided if necessary, but not mandatory. So these lines are primarily used for accessing memory and input output devices. Obviously, the most important lines are address lines, which I have not mentioned. And data lines. So apart from address and data lines, these are the memory and IO control lines which are necessary for interfacing memory and input output devices. Then you will require some lines with the help of which the CPU can be controlled from the outside world. Sometimes you may have to interrupt the CPU. You have to send some signal to the CPU so that the bus is relinquished for, say, direct memory access mode of data transfer. So for that purpose, some lines are provided on the interface section as part of the system bus, and these lines can be classified. Some of the lines are reset, interrupts, bus request, bus grant lines. This is necessary to implement, later on we shall discuss in more detail, to implement DMA mode of data transfer, direct memory access mode of data transfer, these lines. And these interrupt lines are necessary to implement interrupt driven data transfer. So these are some of the CPU and bus control lines. Apart from these lines, you will require utility lines like power supply lines, VCC, ground. You will require some clock lines, because you will see that microprocessor is nothing but a sequential circuit. So you will require some clock for its operation. So there should be some clock input, or if not clock input, some input for connection of pistol. Oscillator circuit may be inside the chip, but you have to connect pistol from the outside, which cannot be fabricated on an IC, so that the circuit, the internal circuitry operates at the pistol frequency. Then you will require some special type of IO lines, serial IO lines sometimes. So these are the typical uh, signals which are provided as part of the interface section, and which we may call as the system bus for interfacing to the memory and input output devices. Let us see which is provided in 8085. This is the 8085 microprocessor. As I told, it is provided with 40 pins, and on these 40 pins you have got AD0 to 7. This is your address, data lines. As I told you, to optimize the usage of the number of pins, some pins are used for dual purpose. Here are those lines. AD stands for address and data. That means same lines are used to generate address, same lines are used for receiving data or transferring data to the outside world, to or from the outside world. memory and input output devices. And so D0 to 7 is the data lines, it is available here. Then A0 to 7, and here you have got A8 to 15. So these two together provides you 16-bit address and 8-bit data. So instead of 24 pins required here, you are managing with 16 lines by using this multiplexed address data lines. This is what you are doing is multiplexing, time division multiplexing. So for some duration of time, you are using those lines for transferring address. For some duration of time, you are using those lines for transferring data. And these are the lines, as I told, are used for memory and I/O control. So here two separate lines are provided for read and write. This is for uh, uh, informing the outside world that the signal, the address that is generated is for I/O or for memory. And this is that address latch enable, which tells whether on these lines you have got address or data. Whenever this is active, that means here you have got address. When it is not active, that means you have got data lines. The ready input, as I told, it is used for interfacing with slow memory devices. Then you have got some status lines, which are provided to the outside to indicate at what state the microprocessor is working now. And these are the lines which are essentially CPU and bus control. All these lines, trap, RST 7.5, RST 6.5, RST 5.5, INTR, these are all interrupt inputs. So 8085 has got a very powerful interrupt structure, a number of interrupt lines. Later on we shall discuss in detail, and we shall see that a microprocessor must be provided with at least two interrupt inputs. One is known as non-maskable interrupt, which cannot be masked. Another has to be maskable. And in case of 8085, trap is that non-maskable interrupt. On the other hand, RST 7.5, 5.5, 6.5, INTR, these are all maskable interrupts. By that we mean, by programming, those interrupts can be ignored or disabled, but trap cannot be disabled or ignored. Then this is your reset in, reset out for resetting purpose. Whenever you reset the microprocessor, it goes to a predefined state, and reset out is the signal coming out from the microprocessor. Whenever you activate reset, this reset out comes, indicating that reset has taken place within the microprocessor. This hold and hold acknowledge, these are those bus control lines. Essentially, this is the DMA request, and this is the DMA grant, direct memory access request line, and this is the direct memory access grant line. Later on, when we shall discuss the DMA mode of data transfer, we shall see how these lines are used for that purpose. And these are the crystal inputs. And SID and SOD are used for serial mode of data transfer, serial IO lines. Obviously, apart from this, you will require VCC, that is your plus 5 volt, and VSS is connected to ground. So this here we have shown all the interface lines which are used for interfacing the microprocessor to the outside world. Now, timing and control unit. This section we have not yet discussed. What the timing and control unit does? Timing and control unit coordinates and controls all internal devices, internal uh, units. What are those units? ALU, resistors, all these are controlled by the timing and control unit. Not only that, timing and control unit also controls the external world. It receives some signal from the external world and also generates control signal. Later on, we will see that timing and control is nothing but a finite state machine, FSM, finite state machine. Finite state machine, this is the general block diagram of an FSM. It receives some input, primary input. It generates some output, and it has got some memory elements, and these are the internal states. This is the general block diagram of a finite state machine, FSM. And basic structure, the way the control unit operates, acts like FSM. You will see that it will receive some inputs like the inputs that I have discussed. Those inputs coming from, say, hold acknowledge, hold request, interrupts, and also some inputs will be coming after decoding that instruction. And in return, it will generate control signals to control all the different sections, the registers, ALU. It will also generate control signals for memory and input-output devices. Anyway, in this class, we shall not go into the details how the control unit is decided, but we shall see how it works, how it is controlling the memory and input-output devices. We shall do that in the next class. But before I conclude, let me just give a block diagram of 8085, that internal block diagram. I have already discussed what is provided inside. This is your accumulator. There is an internal bus, internal data bus, to which all the resistors, this is your accumulator, temporary resistors. I was telling about that one temp resistor, which is not accessible to the user. And this is the accumulator. One of the operand always comes from this particular accumulator. And this is that ALU, arithmetic and logic unit. And this is that flag registers where those 5 flags are stored, which can be accessed to the data bus. And this is that instruction register, which is not accessible to the user, but once the instruction is fetched from the external world, from the memory, it is stored in that instruction register. It is decoded with the help of this instruction decoder. Then the signal goes to the timing and control unit. You can see here the timing and control unit is receiving inputs from the instruction decode unit. It is also receiving input from the ready, the reset, and also it is receiving inputs from those interrupt signals which are not shown here. And accordingly, it is generating various control signals. All the lines are not shown to avoid complexity of this diagram. Then this is your reset in, reset out. And to this internal bus, there are 2 buffers. Those address bus and address data bus buffers are provided, which are connected to the outside world, to memory and input-output devices. So this particular figure gives you the block diagram of 8085. So in the next lecture, we shall discuss in more detail about the timing and control unit, how it operates, how it fetches instructions from the memory, how it executes it, and so on. So we can summarize what we have discussed today. Today we have introduced to you the architecture and organization of 8085, particularly the register unit. What are the different types of registers available inside the 8085? We have discussed in detail the interface section, which is used as system bus for interfacing to memory and input-output devices. We have also discussed briefly the function of the timing and control unit, and in the next class we shall discuss in more detail the function of the timing and control unit. Thank you. So from next class, come little ahead of time, so that it will be here only. I shall try to do it here, and if I am not able to ready, I mean, if